Okay, so this is the part 2 of practice session. This is a part 2 of numericals practice session. Okay, so let's begin with the question. Okay, so here we are taking the formula of closed system. This is the formula of closed system. Okay, this is a formula of closed system. Okay, you guys have to note it down with me. Okay, note it down this full portion. Okay, this one, everything you have to note it down with me. Okay, so this is a formula of closed system. This is a formula of closed system. So in volume 1, suppose this is a concept. Take the variables. Take the given variables from the question. Okay, here the initial volume 1, or means initial volume is 2 meter cube. Final volume is 6 meter cube. The final volume is 6 meter cube. Okay, so what is the work done when the volume changes from 2 meter cube to 6 meter cube? Okay, what is the work done? What is the work done when volume changes from 2 meter cube to 6 meter cube? So how much work is done when the volume is becoming 2 meter cube to 6 meter cube? Okay, so we have to calculate. So open the calculator. We have to calculate this question, man. Let's solve it, man. We have to solve. Okay, W122 here from 2 to 3. Okay, from 2 to not 2 to 3, not from 2 to 6. Okay, from 2 to 6, like this. That's 6, this. Okay, and the formula is what? The work done formula is delta P dV. This is V2 and V1. Here is the formula. Here is the formula of closed system. Okay, so minus 3V plus 16 into 10 to the power 5 dV. Okay, dV, and this is okay. Okay, note it down with me. Then this is occurring minus 3 V square by 2 plus 16V factor. 16V. Okay, 16V, and the 6 and 2. Okay, this is limitation. So now 10 to the power 5 minus 3 by 2 into 6 square minus what? 2 square. 6 square minus 2 square plus 16 into 6 minus 2 plus 16 into 6 minus 2. Okay, 16 into 6 minus 2. So what is coming? Minus 3 to the power 2. Solve it. I have to calculate. I have also my calculator here. Minus 3 by 2, 6 square minus 2 square, 6 by 2. Okay, so the answer is, you know, everything is cutting down. So 1 bar. No. You have to calculate, you know, the answer is not you have to solve this. Oh yes, you have to solve this. This is not the answer. 1 bar, not this is one, not this one. You have to calculate this. You have to calculate. I will not calculate for you. Okay. So let's go to the next question. I hope you understood this question. I didn't solve it. But I hope you guys will solve it. Okay, because I haven't my calculator here. Okay, I haven't my calculator here, so I can't calculate. Okay, so the next question we will do. Please don't mind. I am not calculating. Please don't mind for me. Okay. Okay. Yeah, this one is question number 5. You have to know. Okay, 3 moles of an ideal gas. 3 moles of an ideal gas are compressed to half the initial volume at a constant temperature of 300 Kelvin. At a constant temperature of 300 Kelvin, the work done in the process is what? So this question I already solved it. Okay, so that's why I have the answer in my copy. Okay, so the work done in the process is, first one, A, 5188 kilojoule, 5188 kilojoule, and the B is 2500 kilojoule, 2500 kilojoule. Okay, 2500 kilojoule. C minus 2500 kilojoule, and the D is minus 5188 kilojoule. Okay, note it down fast. Fast. You have to note. Okay. What is the question? 3 moles of an ideal gas are compressed to half the initial volume at a constant temperature of 300 Kelvin. The work done in the process is what? The work done in this process is what? 3 moles of an ideal gas. Suppose 3 moles of an ideal gas, 3 moles of an ideal gas will compress it. Okay, I hope you guys note it down. I am giving you 1 minute. Okay, I hope you guys noted it. So let's solve it, man. Okay, so here the question is 3 moles of an ideal gas, 3 moles of an ideal gas, 3 moles of an ideal gas are compressed, 3 moles of an ideal gas are compressed. Suppose this is a container. Suppose this is a container. Here is a piston. Here is a piston. Okay? Here is a piston, and here is some gas. Okay? Here is some amount of gas which is 3 mole. Which is 3 mole. Which is 3 mole, okay? And now here the question is saying we are compressing the gas. The next step, we are compressing the gas at the container, and we are compressing the gas. That means here. That means here. Okay? Means suppose the initial state is first step. Suppose the initial volume is this, and we are displacing this piston. Suppose we are displacing this piston to this point. That means the displacement of this much distance occurs. Okay, displacement occurs of the pistons, and the moles of the gas become 3/2 mole gas. Okay, this is the question that we are compressing the gas through piston or anything, and the initial mole is 3 mole, and after compressing the mole is becoming 3/2, means half. 3/2 half. That means 1.5. Okay, the mole becomes 1.5, which is 1.5. Okay, so this is the question. And we have to find out the work done in this process. So how much work is done during this process of compression? Like the initial state is this. First initial state is this, and we are compressing. Suppose this is the initial state. And we are compressing this piston to second point, this point. Okay, so this is the initial state and this is the final state. Okay, so how much work is done during this compression process, like from this point, from going the piston from this point to this point, how much work is done on this process when the piston is going from first point to the second point? So that we have to find out how much work is done. Okay, so let's start finding out. I hope you all understood the question. So one thing I want to tell you, that if you want to solve a numerical question or any theoretical question, first you have to understand the question, then only you can solve it. Okay, so I think you all guys have understood. Then let's go to the solving part. Okay, let's go to the solving part. We will together solve it. here the second value is also telling that this this process is occurring in constant temperature. Constant temperature. Okay, this process is occurring in constant temperature. Constant temperature. So this is an isothermal process. Isothermal process. Okay, this is an isothermal process. Got it? This is an isothermal process. Iso means what? Constant, and thermal means temperature. Okay, so this is an isothermal process, means the constant temperature. So this process is occurring in constant temperature. So we have to use this formula. 1 to 2 means what? 1 to 2 means here piston is like this is a piston. Like this is a piston. This is an initial state. This is the initial state. Okay, and this is the initial state, and this is his final state. Okay, so there's a final state. So it is going from 1 to 2. Okay, from initial state to final state. Then that's why here we are denoting 1 1 2. This is not 12. Okay, this is not 12. This is 1 to 2. This is this. This is 1 to 2. Okay, this is 1 to 2. This is not 12. This is 1 to 2. So the formula is the piston is going from initial state to final state. So the P1 V1 natural log of V2 by V1. Natural log of V2 by V1. Okay. So PV is equal to, we know that PV is equal to MRT. We know that PV is equal to MRT. So natural log of V2 by V1. Here we have to PV is equal to MRT. PV is equal to, okay, you have to guys, you have to note it down with me. Okay, from this part the solving part is going. Okay, from this part the solving part is starting, and this is the conceptual part. We are understanding the question. Okay, we were understanding the question. Okay, so then nRT, this is a characteristic gas constant. This R means characteristic gas constant. Okay. Okay, so this one is characteristic gas constant. Okay, so then Ln V2 by V1. Okay, so guys, I want to tell you this R means characteristic gas constant, and this R means specific gas constant. Okay, this only R means and specific gas constant, and this R means characteristic gas constant. Characteristic gas constant. You have to know this thing. Okay, this R means R is characteristic gas constant, and this R means specific gas constant. Okay, so this is enough. Okay, so now this happened, and then 3 into the value of universal gas constant or characteristic gas constant is 8.314. 8.314 into 300, and natural log of 1 by 2. Natural log of 1 by 2. And the final answer will be minus of 5188 kg. Okay. Okay, so what is this minus sign is denoting? This minus sign is denoting the compression work. Okay, like we're compressing the piston, we're compressing the gas. That is denoting this minus sign. Okay, the minus sign is denoting that. So this means compression work. Compression. This sign is compression work. Okay, so note it down, guys. Okay, hope you guys note it. Okay, guys, if you are liking this video, I know I'm in the beginning stage, like I'm a beginner in teaching, so there is something mistakes are happening. Some mistakes are happening. Okay, so you have to forgive me for that. But if you like my session, if you are liking my session, then please like, share and subscribe my channel. Okay, so that's all I want to say. Okay, let's go to the next question. Okay, so this question is little big, but the solution is very easy, very interesting and very easy. Okay, so these are the clean questions of basic thermodynamics. Okay, these are very clean questions. An ideal gas undergoes an ideal gas undergoes an isothermal expansion. Isothermal expansion from state R to state S. From state R to state S in a turbine. In a turbine as shown in the diagram. As shown in the diagram. Okay, so we have to draw the diagram also, man. We have to draw the diagram also. Analytic gas 100% isothermal expansion from state R to state S in a turbine. In a turbine as shown in the diagram given. We have to draw the diagram. Oh my god. Yeah. Given the area of labeled region, area of labeled region is 1000 Newton per meter. 1000 Newton per meter. So what is the amount of turbines? What is the amount of turbine? What is the amount of turbine work done? What is the amount of turbine work done during the process? During the process. What is the amount of turbine work done during the process? Okay. So option A is 14,000 Newton meter. B 12,000 Newton meter. 12,000 Newton meter. B 12,000 Newton meter. C 11,000 Newton meter. C 11,000 Newton meter. 11,000 Newton meter. D 10,000 Newton meter. Man, this is a very interesting question, man. So note it down fast. The question is saying an ideal gas undergoes an isothermal expansion from state R to state S in a turbine as shown in the diagram. Given the area of level region is 1000 Newton per meter. Given the area of level region is 1000 Newton per meter. What is the amount of turbine work done? What is the amount of turbine work done during the process? What is the amount of turbine work done during the process? Option is this. Okay. So we have to find out the work done by turbine. So you are seeing that work done type question is coming so much. Okay. So the formula of work done, like formula of the work done formula for closed system, for open system, you have to remember. Okay, you have to remember those formulas. Okay, then you can solve this question. So I hope you guys got it. Let's solve it. Okay, solve it. Okay, the diagram is this, this, this. Okay. Okay. So this is what it is. Thousand. Okay, so this is the diagram. This is the diagram. Here the question in question, we have given the area of level region. The area of level region is 1000 Newton into meter. So this is the level region. This is the total level region. Okay, are you guys saying this is the total level region? This one. This is the total level region. This one, level region. Okay, this is the level region and the work done. The work done in that level region is 1000 Newton into meter. The work done in the level region is 1000 Newton into meter. 1000 Newton into meter. Okay. Okay. So we have to find out an ideal gas undergoes an isothermal expansion. An ideal gas undergoes an isothermal expansion from state R to state S. From state R to state S. Okay, work done. So we have to find out the work done during the isothermal expansion of work done expansion from R to S. Work done is equal to expansion from R to S. Okay, expansion from R to S. So we have to find out what is the work done during the isothermal expansion. Okay, isothermal expansion. This expansion is what? Isothermal. Okay, so this is the isothermal expansion. Oh, that means expansion is doesn't matter which expansion. This is expansion from R to S. Okay, so